The chapter we are on right now is chapter on sound. It is chapter 12.
We're getting pretty far.
Now, when you talk about sound, the first thing that is to be thought about is what causes sound?
Sound waves.
Vibrations. So write it down. Vibrations cause sound. That's point number one. Vibrations are required to cause sound. So if something is made to vibrate, then that vibration is what pushes the sound, pushes the air, and creates compressions and expansions. And that's how sound is generated, sound is produced. So when you hear of any sound, it's all caused by vibrations. What kind of a wave is sound wave? Transverse or longitudinal? Longitudinal. It is longitudinal. And by saying it's longitudinal, it's made up of compressions and expansions. And when you say compressions and expansions, the waves are going to be created like this. Particles of air are getting pushed, Thomas. So the particles are, it's getting compressed and then expands and then compressed and then expands and then compressed and then expands and then compressed and expands. That is how compressions and expansion go. So here is compression, compression, compression. And these are expansions, 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 expansions. What is the distance from one compression to the next compression called?
No. With half a wavelength.
Wavelength. Symbolized by the letter lambda. Lambda is the wavelength. It's also same thing as from one expansion to the next expansion. That's also wavelength. From one expansion to the next expansion, or from one compression to the next compression, that's called wavelength. So sound propagates by this method, and you know the equation that we use is this: velocity is equal to f lambda. Velocity is, or the speed, how fast the sound waves go, depends on frequency and lambda. Now the connection between frequency and lambda is this: if I increase the frequency, like instead of pushing the air particles like this, step by step, if I increase the frequency and push it more often, then this is what's going to happen: compression, 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 compression. So what's happening here is compression. What do you see as a wavelength? Shorter. And this is a bigger wavelength. That's a shorter wavelength. But this one has more frequency. What do you mean by frequency?
The rate.
The number of compressions produced per second. The number of compressions produced per second. That's called frequency. Right? This is bigger frequency. This one's frequency is smaller. That means if the velocity of sound is a constant, like in this room, the velocity of sound is going to be constant. The frequency, if it's a small frequency, then the wavelength is big. If it is a big frequency, then the wavelength is small. It is inversely proportional. Frequency and wavelength are inversely proportional. Do you understand that? Frequency and wavelength are inversely proportional. Just to give you an example, imagine if there is a lady squeaking at a high frequency here, and I'm talking to you with a frequency here. Who has got a bigger wavelength?
And you.
I've got a lower frequency. The lady has a higher frequency but a shorter wave. So this is like the lady's voice. This is like my voice, right? My voice has got a lower frequency but has a larger wavelength. It's almost that much. When I'm talking, the wavelength is from here to here. So if one compression is here, the next compression is there, and so on. So you're listening to those compressions through your ears. But for the lady, the compressions could be that close because the frequency is higher. So more number of waves are produced per time. So that's why the frequency is higher. Now this speed depends on what factor? Speed depends on medium. The speed depends on the medium. Which means, is a sound wave going through air? Or is a sound wave going through water? Or is a sound wave going through steel? That makes a big difference. In addition to that, the medium's characteristics are different at different temperatures. That means in under cold temperatures, speed of sound is lower. When it is hot, speed of sound is higher because the particles are already energetic.
So when you say a medium is blank based on its temperature, what do you say it was?
The medium depends, the speed of the medium depends on the temperature also.
Okay.
Like speed of sound in air is not one value. When it is cold, it is low. When it is hot, it is higher by a little bit. For every degree rise in temperature, the speed of sound changes by like 0.6 meters per second. That's the connection. So on a summer day, the waves can go faster. Winter day, waves don't go that fast. Okay? Depends on how many degrees it is low. Like, imagine I'm passing the message to you all and you just woke up from sleep. You hardly have any energy. So the message is going to be passed slowly. On the other hand, imagine you have a lot of energy, you are hyper. At that time, if I pass a message, it can go faster because you are already agitated, right? And therefore, it is easier to pass the energy. So when the temperature is higher, it goes faster. And speed depends on the medium, that being said, waves cannot go through vacuum. Sound waves cannot pass through vacuum. Did you get it? Sound waves cannot pass through vacuum. So the main points are here: vibrations cause a sound. They're all longitudinal waves only, no transfers. Sound cannot go like this. Sound cannot make crest and trough. So longitudinal waves are made up of compressions and expansions. The distance between two compressions is called a wavelength. And the number of waves generated per second is called frequency. The connection between frequency and wavelength is inverse proportion. When the frequency goes up, the wavelength goes down, and vice versa. And then you saw the speed depends on the medium. The velocity of sound depends purely on the medium. And how waves actually travel from one place to another place. How does a wave travel from one place to another place? This is the place where the sound is produced, just produced. In other words, I'm just creating the sound like that. When I create that compression, what happens is the compression is going to start traveling, right? Compression is going to travel in all directions. So this compression is going to travel in all directions. After a certain period of time, this compression must have gone till this far. So the compression has gone here, compression has gone here, compression has gone here, everywhere, all around. So this is a source of where the compression was initially started, and then the compression travels till there. How far will a wave move in one time period? Can you look back into your notes and find out? How far will a wave go in one time period? One wavelength. Very good. So, if it takes one time period for this wave to go here, and another time period, this wave will go here. The wave is going here. So these are the compressions. These are the next compressions. What's the distance from here to here? A wavelength. So all these lines that are drawn around, these are called wave fronts. These are called wave fronts. Those are called wave fronts. And the distance from one compression to the next compression is lambda. So these are the wave fronts, just like ripples. If you bob water up and down at one spot, your ripples are produced, right? And the ripples are moving outwards. And you can see those ripples going outward. Of course, that is visible to you because they are transverse waves on water. Sound is not visible because it's made up of compressions and expansions. You can't see it. You can't see the compressions and expansions. Now, if you produced only one pulse wave like this, that's only one pulse. It's not a continuous sound. If it's just one pulse, that pulse is one compression that travels continuously. There's no second compression. But if I produce continuous compressions at a certain frequency, I'm going to get one compression going there, going there.
Acts like a ripple.
Almost like ripples. This is exactly what we do. Now, when I talk, the vocal cords are shaking at a frequency. Mine is shaking at a frequency of roughly 400 hertz, 300, 400 hertz. That's how ours shake. That means that many compressions are produced every second. So you can see that this is the one which I produced initially. This is the next compression I produced after one time period. This is the next one I produced after the next time period, and so on. This is one being produced just then. So these are all called wavefronts. What's a wavefront? Wavefronts are locus of all points produced at the same time. What do you mean by locus? In geometry, you must have come across locus. Locus simply means connecting points, joining the points. So if you join all the points that were produced at the same time, you get a wavefront. So in other words, all these were produced at one time. All these were produced at another time. And all these were produced at another time. And there is one being just produced here. So the wavefronts are locus of all points produced at the same time. If I ask you this question, what is the locus of all the points which are same distance from me? What do you get? What is the locus of all the points same distance from me? What do you get?
Say again.
What is the locus of all the points which are at the same distance from me? What do you get geometrically? What do you get?
Circle.
Circle. So in other words, if from this point, if you take the locus of all the points which are exactly 5 centimeters, you end up getting a circle, right? Because exactly 5 centimeters from here, this is one point, another point, another point, another point. So if you connect all those points together, you get a circle. So the word locus simply means connecting points. Okay? So the locus of all the points produced at the same time is wavefronts. Now when I'm talking, all the waves are going in all directions. So what's the locus of all the points produce the same time? Sphere. It's going in all directions. Now on the surface of water, it can only go two-dimensionally, right? On here it can go in all directions. Do you understand the wavefront concept? What is a wavefront? So when I talk, the sounds are actually going to come to you in the form of wavefronts. It's a wavefronts that causes. Okay? Like when I create a vibration. When I create a vibration like this, now that's a tuning fork. When I create this vibration, what is happening here? The prongs are going forward and backward, creating compressions, expansions, compressions, expansions. How many of them? This is 384. The frequency of this is 384 hertz. So you don't see it shaking, but it's a lot of movement. And if I connect it to the box here, it magnifies it. When you touch it on a surface, it just magnifies the vibrations. Yeah.
You said 384 hertz. So is that like it vibrates like back and forth 384 times?
In 1 second. Yes.
Whoa.
Yeah, 384 times it vibrates in 1 second. Yeah, the bigger the surface area, the more you can expect. Yeah. Now, when I look into a tuning fork, I remember a student long back in the 80s. More than anything else I have to say, I remember an idiot. You know why? Because when I was teaching, no, this is a different one. When I was teaching this, they were supposed to be doing a lab individually. I'm talking about seniors. So they were supposed to be doing lab individually, and the lab was like they had a long glass tube connected to a rubber tubing and all that, and there was water in the tube, and they were supposed to hit this tuning fork and keep it next to the mouth of the glass tube like this, and they were supposed to hear what is known as resonance. You'll be doing that later. Okay, so when the students are now, they were doing individual labs, so they will be given tuning forks, 3 of them, and the setup. Now that setup is expensive because that tube, if it breaks, I have to replace the whole tube. I can't do any, patch up on that. So I have to give this instruction earlier itself, like don't touch the tubes, If you touch the tube will shatter. Like if I'm going to touch this, and so it's got a lot of energy in this, and the tube will break, and if the tube breaks, then I have to replace the entire tube. So it's a headache, and they have to pay for the entire thing. So this is the reason why I kind of tell the students earlier itself, don't do it. And this idiot was actually asking me, what will happen if I touch it on my teeth? And then I told him, I have not tried touching my teeth, but it'll be better if you keep it off. Don't do it. Because our teeth, it's the hardest substance on us. It's got the enamel, it's got dentine, it's something that is brittle but very hard. It's brittle but very hard. But don't test it, So, some people are there who don't listen to wise instructions. They will understand it only by experience. Some of you are like that. If I tell you don't touch that wall, I just painted it, you will just think that, oh, maybe he's just bluffing. Oh, maybe, and then you will just go close and just touch it. Or if I tell you that wall is warm, don't touch it. You will not believe until you go and touch it and, oh, yes, it is warm. All right? Some of you want to believe like St. Thomas. You want to believe by touching. All right. So,
I thought it was that.
What are the odds?
All right. So what happened to this boy?
0 and 0.
When I gave the freedom to kind of go ahead with the experiment, this boy actually took it He hit it, and before even he could start the experiment, he said, no, this will not do anything. He touched it on his hands, so it should not do anything much. And he went straight to his teeth. And then there was a little commotion, and I just said, what is happening there? And the students were saying, oh, he touched on his teeth. I said, oh, okay. I went to him and I asked him, like, what happened? He said, I touched, and how did you feel it? Oh, it was a very sharp kind of a pain thing, but no, I'm fine. There's nothing wrong. I said, show me your teeth. And the front teeth, I checked it, everything seems to be fine. I said, okay, let's go. And then he went on. After a month, that tooth started changing color. It started changing, kind of greenish, bluish sort of color. It changed colors. You know what happened? There was a hairline crack that went right through into his roots, and it killed the tooth. Yeah, and it started like infecting it from inside, and then finally the whole tooth was, after 2 months, it was like almost like dark, and then it had to be extracted, and then he was without his tooth for the rest of the year. He must be walking around even now with artificial implants, because that was his permanent tooth. Anyway, so when I look at this, I remember that person, because some students, kind of, as I said, some students will take the instructions properly and say, all right, don't do it means don't do it.
That's a good form of torture.
Yeah.
Torture?
Tertiary. You said tertiary? Tertiary.
My son actually had this issue also when my second son, when he was learning how to drive and all that, when I was with him. When he drives, I was always like instructing him, don't keep shaking the steering wheel now and then, it goes here and there. And I was not comfortable sitting on the other side. So I was always like tensed. And the other thing he was doing was like getting closer to the other cars, like too close. And I said, why do you want to get so close? There's no reason why you should be this close. Because in case they apply brakes, you should have time to react. So don't keep a distance. And then his response was, like, if I keep a distance and others will get inside. Okay, let them get inside and go on. But you keep going at a normal pace and keep a normal distance, and you'll be the safe driver. So nothing of this instruction worked. When he actually had an issue and he was driving a manual car also, he got onto the highway, went onto this fast track. As soon as he went there, immediately there was a lot of traffic hold up there, and there was a little sleet on the road as well. So he couldn't apply the brakes, because if he applied the brakes, it'll slide and go. So he went off the road onto the pebbles and all those, and then there was railings, guardrails, and those wires. Hit those 3 posts, he just knocked them down. He had to stop the car that way because he couldn't. So the side of the car was completely gone, and it had to be totaled. All that kind of gave him some idea, because he learned only after he experienced it. Now, he should have done it earlier. You know what I'm saying? So nowadays, he's extremely cautious, very cautious. If I'm driving and he's sitting next to me, the moment I try to change my lanes, he's like looking around. He's looking around very carefully. And that is the other type, where people learn through experience and not by wise instruction. So if you're told, don't do this, you should not do it. That's it. Don't try like disobeying that rule. Like if you're told, okay, that stop sign means you have to stop, and stop means stop and go. You just don't slow down and go. That's a rule. So follow the rule. Why do you want to just test if everything is okay by slowing down? One day you'll be caught. And then after that, you'll start slowing down better. Anyway, so the tuning fork is a typical example of that. Now, coming to sound itself. Now, sound is characterized by pitch. Loudness and quality. These are the 3 characteristics of sound. The 3 characteristics of sound are pitch, loudness, and quality. Pitch. relates to frequency. Pitch relates to frequency. And what do you mean by that? You know, pitch is a very common usage. This is the scientific term. Okay? So if you say, oh, he's singing at a higher pitch, that means higher frequency. Singing at lower pitch means lower frequency. And you can hear the pitch and then decide which is low, which is higher. Look at the sound. Look at that. Hear the sound and this. Which is a higher frequency. Yeah, therefore, this is higher pitch. So this is high pitch and that's lower pitch. Everything in this room has, that's got a different pitch. That's got a different pitch. Every pitch is different. Huh?
Computer? Computer screen?
So everything has got different pitch. Now this one has got a standard pitch, which is 384 hertz. So pitch depends on frequency. Loudness depends on amplitude. Loudness depends on amplitude. Now what does that mean? Loudness depends on amplitude. Like if I hit this table, see? Are you able to hear it?
Yeah.
And the pitch is like fixed. Now if I hit like that, are you able to hear better? This is because louder. Now what makes it louder is because when I hit it harder, the vibrations are with a larger amplitude. Now it's not easy, it's easy to show on this one how the amplitude changes, but not in a sound wave, because sound waves are longitudinal, not easy to show the amplitude, but you can actually, you know, like show the amplitude on a normal transverse wave. So that is the amplitude. What is amplitude? The maximum displacement of particles from the mean position, that's called amplitude. The maximum displacement from the mean position, that's called amplitude. Now this is higher amplitude. You see? So this is higher amplitude, that's lower amplitude. So which means if you pluck a guitar string, gentle, very gentle plucking, then its amplitude is going to be less. If you pluck it harder, its amplitude is going to be more. So it's going to be louder. You understand? So if you pluck it gentle, it'll be softer sound. If you pluck it harder, it's going to be louder. So understand that you can have the same pitch, but one can be loud, one can be soft. So you can have two guitars striking the same key, but one is striking it gentle and the other is striking it hard. So with eyes closed, can you tell which one is louder?
Yes.
What helps you to distinguish, so that is called loudness. Okay, you understand this? Now, what is pitch? Pitch is the characteristic which helps you to distinguish two sounds coming with the same loudness, but one is sounding at a higher pitch, frequency. Like guitar, they're both plucking same loudness, but one is plucking the C and the other is plucking the D. Will you be able to say which is high and which is low?
Yeah.
That is this characteristic. So we are talking about sound characteristics. Quality. Quality depends on what?
Quality.
On waveform. Quality depends on waveform. Now what is a waveform? Like in a transverse wave, it's easy to show the waveform. But in a longitudinal wave, it is not easy to show the waveform because it is one-dimensional. So if this is a wave form, this waveform is a very smooth wave. If a wave is like this, it comes either from a flute or from a tuning fork. So this, when I hit this, the sound that's coming out is smooth like this. Now, if it is coming from a violin, The same sound, if it's coming from a violin, it'll be like. See, you can see the wave is exactly there, just like this. But there's a lot of spikes. So when you play the violin, is it totally sounding different? Even if it is the same pitch? Yes? So if the same pitch is played by a violin, can you just close your eyes and say, yeah, that's a violin, this is a tuning fork. What helps you to distinguish it is this quality. Now, an organ will be probably like this. Something like that. So that may be an organ sound. Each instrument has a unique quality. You understand that? Each instrument has a unique quality, its own characteristics. Each instrument has a unique, same way as your sound. Is your sound having unique characteristics? Yes. Your sound has a very special place. That is, your quality is not matched by anybody else. That is what is used in voice recognition softwares. Your sound quality is yours. Like when I talk, I've got that quality of sound. That's mine. Even without looking at me, you can understand the voice is coming from me. Hasn't it happened before? Like someone calls you on the phone, you don't even see who's calling, but the person actually says, hello, how are you? Immediately you know who it is. You just heard only the sound and you can recognize that person straight away. How are you able to recognize? I mean, so many times it happens in the corridors. Yeah, lunchtime, someone is behind me and he's talking, and I'm thinking like, that seems like this person. And I look around, yeah, it is that. Because unique sound, sounds. So everyone here has a unique frequency.
Yeah.
Unique frequency. That means like not matching at all. We're going to do an exercise right now. Can you look around and tell me who knows the name of everybody else here? Just.
Ken, what's your name?
Evan.
Everyone's okay?
Yeah.
If anybody wants to volunteer.
I'll volunteer.
Okay, come on, Will.
I'm just too good.
Let me.
Wait, am I going to be in the video now?
I can't put you on the video.
No, don't put me in the video.
Okay. So good job, Will. Now, how is that Will identified everyone's voice so perfectly? Is because our brains are marvelous. I'm telling you this.
Tommy, I lost your pen.
Our brain is like a computer. Listen up. Our brains, sit down. Our brains are like computers. Like he's got a separate folder for everyone. In his brain, he's got a separate folder for everyone. So, and in that folder, the name of the person, the picture of the person, the voice is recorded, and all the all the experiences that he has with him, it's all documented there. As soon as he hears the voice, immediately the message goes into the ears, longitudinal waves going and hitting the ears, and that message goes to the brain, and the brain immediately opens up the right folder and then tells him that this is a name. It's amazing how the brain is able to detect, how the brain is able to see where the thing is coming from and all that. That is amazing. All right, so this characteristic. So what are the three characteristics? One is pitch. What is pitch? Pitch is the ability for us to, what enables us to distinguish two sounds even though the loudness and quality are same. In other words, violin, violin. Same loudness. But one is playing the C and one is playing the D. You can distinguish it. What is this characteristic? Violin, violin. Both frequencies are same, but one is playing gentle, one is playing harder. So you can easily close eyes and say which is louder. What is this one? This one is playing the same note C, playing the same note C, playing the same loudness, playing the same loudness. But one is a flute, the other is a violin. How your brain is able to say which is a violin, which is a flute, That is quality. In fact, a lot of sounds that we hear normally, they're all recorded in your brain. That's how when you hear a bird chirping, you may be able to say what bird it is also. Like, it's recorded. Okay, so you are able to record all these things. So not only the verbal sounds from anything, like if I drop a ping pong ball like that and you didn't see what is dropped, by hearing the sound, you will immediately know that it's a ping pong ball that is bouncing. Right? You can figure it out. You can figure out what exactly is happening. That's called quality. Now, most of the voice, recognition softwares, they work on the quality. So this waveform is, so everyone has a different waveform. I'll show this to you later on. Like, I'll give you a microphone and you just talk into it and you can see your wave. And you can see everyone's wave is different. In the sense, like if you say, ooh, everyone's ooh is going to be different. Everyone's waveform is going to be different. Not here, on the microphone. Do you understand? Okay. I'll show that to you later. I'll show that to you later. Like, if you're going to talk into a microphone, giving one tone, and that one tone will have different shapes. And what the voice recognition software does, it takes that, digitizes it, and then makes it into a barcode kind of thing. And then it is waiting for that. So the moment you say, hey Siri, then it opens up. Somebody else who says that, it doesn't open. Because it actually recognizes your voice and it tries to match up the quality. All right.
You have to say it like really loud. I was 6.
Now the pitch, which depends on frequency, is classified into 3 main classifications. 0 to 20 hertz. 0 hertz to 20 hertz is your first classification. 20 hertz to 20,000 hertz is the next classification. 20,000 hertz and above is our third classification in terms of frequency. So the frequency of this tuning fork is 384. Where is it coming under?
In between 20 and 20,000.
This is where it is coming, and this is called the audible range. So anything between 20 hertz and 20,000 hertz is something that is audible to humans. The different creatures have different ranges. Dogs, they won't hear too low frequencies, but they can actually listen to a little bit of this side. Bats, dogs, and all that. Now this range is below 20 hertz, something that we cannot hear, and this is called infrasonic. Infrasonic sound. And this one, that range, what is that called? Ultrasound. Ultrasonic frequencies, 20,000 hertz and above, is called ultrasound. We are not supposed to be hearing it. Infrasonic sounds, we cannot hear it. Some animals produce this, like giraffes, elephants. They have heavier vocal cords, longer vocal cords, so they can actually produce those low frequency sounds. In fact, researchers found out that elephants talk to each other with a frequency which is lower than what we can hear. So even though you see elephants standing here and there, they are actually communicating, but you cannot hear it. Yeah.
So it's 20,000 eyes so we can catch.
Yes. I'm going to show it right now.
Can we barely hear it?
All right, listen. Pay attention, pay attention, pay attention. This is our audible range, and this is the audible range when we were born. Okay, fresh. Right now, this is not your range. Right now, I can say your range should be around from 60 to 70 hertz. From there onwards to 18,000. That's your range. My range is this. I'm also hearing almost from here to 10,000.
Could you play an ultrasonic sound?
Yeah, I will. Wait.
You couldn't hear it.
This is my range.
If I speak at 11,000 hertz, can you not hear me?
I can't.
I'm aware.
The higher part of it is affected by age. The older you go, this number will drop. My father is 89 now, and his range I checked 2 years back. I checked this range and he was 5,000.
Dang.
So the highest he could hear is 5,000. If I put anything more than 5,000, he cannot hear it. But lower frequencies are okay.
How high is 5,000?
I'll play it right now. Yes.
What's the highest?
So like with hearing aids and stuff, is it like what? How does that work?
Hearing aid is just amplitude.
It just affects the
It's an amplifier. So hearing aid, what it does is, because your eardrums are kind of not really sensitive to vibrations, in order to make it vibrate more, you have to pump in more. So you're making the compressions and expansions a little stronger.
So is it hearing aid just affecting the loudness?
Loudness.
Is hearing aid just kind of like a microphone?
Exactly. It's just a microphone. Simple as that.
So why do some of them like not work? Like
Because once, even if, suppose there is a disconnection between the eardrum and the brain, then of course nothing can happen. Yeah, my aunt had issues like that. She was 92 and she could not hear a bit of anything. And what I did helped her a little bit before she died. So what I did was this. I took computer speakers. She was a nun. And my mom actually corresponds with her through a telephone. But my aunt knows at 8 o'clock sharp, my mom calls every day. All right? So she's anticipating the call. As soon as the phone kind of buzzes, she knows it's my mom. And she picks the phone and she says some information from that side. And my mom knows that whatever she says doesn't really go that side, to her. So my mom tries to talk, but it doesn't work. So she just hears, and one person talks, and finally, okay, all right, take care, bye. No, there's hardly any correspondence. And when I saw this thing, I said, no, something has to change here. She is not able to hear my mom at all. And she's just kind of waiting for the call, and imagine like she can hear it. How nice it'll be. So I went, I bought a special cell phone, and I took the output of the cell phone, simple. I took the output of the cell phone. I took a cell phone which has got the jack, the audio, because the one which she was using was not having that facility. So I took one, bought one, changed the cell phone. I took computer speakers. And I connected this into the amplifier. So the computer speakers were blaring the sound like anything. And what she had to do when the phone call comes is like plug it there and take these speakers and keep it next to her. Simple as that. And when she's actually listening to it, like maybe in the cafeteria you'll hear the sound. That loud it is.
Good Lord.
Yeah, the loudness was. So when I was there, I initiated the call between both of them. I said, okay, now I'm going to tell my mom to call this way. And she's going to pick it up. And I told her exactly by writing what she should do when she gets a call. Plug it in, take this, keep it like that, and talk. And I was standing and observing it. It was my happiest day, actually. Because the phone call came, she actually saw this buzzing, and she plugged it in the way I told her, and then my mom's voice was coming out, blaring into the speakers. She kept it like this, and she was able to hear. And then she started talking, and then I said, oh wow, that is amazing, because they are able to communicate. And then I told my mom she can listen, just talk properly. And then my mom was asking, okay, is it raining there? And she says, no, it's rained only 2 days back, and all that stuff. And it was real communication, and both were pleased. And then, and after that, she messed up, and I left that place. I actually flew to her place just for providing this gadget, just for that. And they were using that for correspondence for some time. And after that, somehow the speakers were not working, and then she stopped using it because the speakers are not working. And these nuns, like they just, when something doesn't work, and just keeps it away. And other sisters are also not really helpful there. And it stopped working. And when I was here, I came to know that, okay, it's not working anymore. And I said, okay, now somebody should take care of that, like it's a simple thing. But nobody's there. The next time I went back again to visit her, and I fixed it for her, and I said, use this. And she said, no, I don't want to use it anymore. How long am I going to live? That's exactly how she said, how long am I going to live? So I'm not going to use it. She was 92. So I don't want to use it. So you take it away. Please take it away. Please. I was getting frustrated, by her very strong kind of repulsion there. She was telling no, you just take it away. I don't want it here. You just take it away, because I won't be able to use it. I'm not going to live that long. That kind of a talk. And I said, no, you can use it. You use it. And finally, I handed over those things to the sister and said, okay, after I'm gone, one day just try to connect it and then, do it. You won't believe, after a month or so, she died. So, yeah, she died after that. So, which means she was almost sensing that it is almost finishing. So, yeah, she died after she fell down in a room and then collapsed. But I'm glad now that there was some correspondence. After a long time, they were able to talk to each other. All right, so coming back to this, audible range for me is this. As I grow older, this is going to come down. That's the same case for you. That's why you're 18,000 now, not 20,000 as before. Okay, some of you are probably on 17,000 now. It changes. In fact, there was an open house we had once, and during the open house, what I did was I connected the speaker systems, which I'm doing to do right now. I connected this system, and I told the parents and students, tell me when you don't hear it. And a student, when it reached 7,000, the upper one, 7,000, and even the parents were able to hear it. The student raised his hand saying, I can't hear it. I said, and he was an incoming freshman. He cannot hear it. And I said, again I went back, and again I went on increasing it, and he said, I can't hear it. So I told the father, there is some issue. Take him to a doctor and then get him tested properly. And the dad was very pleased with me, saying that, so many medical checkups were done on him throughout, all physical and all those things, but no one detected this problem of his. But it's just a detection. So I'm going to show you something here. You can actually see it from there. All right, this way. All right, do you hear the sound first of all?
No.
For what?
You don't hear the sound? No, because the frequency is 1 hertz. 1. Can you see the cone moving?
Yeah.
No.
It's like breathing. It's going in and out.
Yeah.
Yeah, I see it.
Watch it carefully.
Oh yeah.
That's cool.
Check the edges, you'll see it.
What the heck?
That's so weird.
It looks like it has life. And you can see it moving faster. This is 1 hertz. I'm changing it to 2 hertz. Is it moving faster?
Yeah.
You can come close if you want to see.
Not by much, but yeah, it is.
If you cannot see it, just come closer and have a look at it. That is 2 hertz, 2 times in 1 second. Can you see it? Check the edges.
Oh, okay.
Yeah?
Yeah.
It's moving, but you cannot hear the sound because it's too low. So I'm going to increase it now. So that is 2 hertz. That's 2 hertz. That is 3, 4, 5, 6, 7, 8, 9, 10 hertz. Can you see it vibrating?
Yeah. Yeah.
And this is not going to give you a sound. It's vibrating. You can see the vibrations there. Right? You can see how it is like shivering there. So this is 10 hertz. I can increase it to 12, 14, 16, 18, 20. That's 20. You see it? Vibration? Yeah. It's vibrating. You can see the vibrations right there. So that's 20 hertz. You're supposed to listen to this, but we can't. Because as I said, the range has changed now. Now I'm going to go higher. That's 20. That's 20. That is 30. That is 40. Let me know when you first hear the sound. 40 hertz. 50 hertz. 60 hertz. You hear now? Yeah, you should be able to hear 60, 70 in that region. 60 hertz. 70 hertz. Yes?
No.
I'll turn it off and turn it on, then you should be able to hear it better. I'll turn it on again. I'm going to turn it on. Okay? That is 80 hertz. 80. Gone. You know why? Because you're using earphones. That's why. If you misuse your ears, this range is going to be cut off. The heavier music you pump into your ears, the low frequencies will be off. You won't enjoy the bass anymore. So it's a warning for you. Don't use earphones. If you can avoid it, avoid it. And if you want to use it, use the lowest volume. Okay? So I think some of you are already messed up. Because this is 80 hertz. 90 hertz.
I hear it now.
You hear now?
Yeah.
Thomas? No?
It's supposed to sound like.
That sounds a lot. Look.
It's just like
I'm turning. It's a humming.
I heard it.
I'm turning it off now.
Shut.
Oh, I hear it. I hear it. I hear it.
You heard it?
I hear it now.
Okay.
It's
That
like a
is-
low hum.
Yes, 100 hertz. You should have heard it long back. Now, this is 120,
Now I hear it.
Yeah, I hear it.
130, 140, 150, 160, 170, 200.
No.
If you cannot hear this, you should go to a doctor.
You can't hear that.
Hey, it's just bluffing. That is 200, 300, 400, 500, 600, 700, 800, 900, 1,000, 1,100, 1,200, 1,200, 1,400, 2,000. Can you hear it?
Yeah.
Yeah.
That's 2,000 hertz, which is almost the same frequency that comes from the spin cap. You hear?
Yeah.
Almost matching up?
Jesus.
Okay, that is 2,000. This is 2,000. Now let's go for the high ranges. 3,000, 4,000, 5,000, 6,000. Now my dad cannot hear this.
What?
6,000, he cannot hear this. And this 7,000, you hear it?
Yeah.
8,000, 9,000, 10,000. You hear it?
Yeah.
I'm almost done.
Barely.
Almost. You barely hear it?
It's getting lower for me.
Yeah, but you still hear it.
Yeah, I still hear it.
This is 11,000, I'm done. I cannot hear this at all.
I hear it.
I can still hear it.
Still hear it?
Yeah.
Is it loud?
Yeah, it's loud to me.
Oh, yeah.
Keep going.
Keep
Okay. 13,
Yeah.
this is 12, this is 13,000.
Yeah.
14,000. Tell me when you cannot hear. This is 14,000. As I said, this will only be affected by age, so you should be able to hear. 14,000, okay?
Yeah.
15,000.
Yeah.
You can't hear?
Yes. I can hear it now.
I can still hear it.
Yeah.
I hear it. I barely hear it.
You barely hear it. Some of you say it's very audible.
Keep going.
You can see how the ranges are changed now. 16,000.
I hear it. Yeah.
Yeah,
I
you're
can
going.
hear it just the way it is.
Yep.
17,000.
I can hear it, but it hurts.
No.
Yeah.
Oh,
See, look.
a little bit.
It hurts for him.
It
hurts.
I hear it
Go.
every now and again. I can't hear it.
18,000, 19,000, 20,000. You cannot hear it now.
I stopped at 19. Yeah, I stopped at 19.